preference relationship from the schools that were ranked. So if I rank school A above school B, I prefer school A to school B. Now, if I didn't rank school C, I don't know if I prefer school C to school A or if I prefer school A to school C. I didn't rank school C, so I can't tell you off the bat how I rank C in comparison to A and B. Okay, so there are several approaches that have been proposed, and in particular, they are basically tailored to a specific empirical setting. Okay, so you can assume that any ranked school is preferred to any non-ranked school. That is assuming that people didn't skip the list. And sometimes when the lists are sufficiently big, and you say, look, yeah, there are 600 schools, but people really don't rank schools that are on the other side of New York, right? All of a sudden you say, well, maybe the 12 schools that they had to rank are not, it's not so bad. So yeah, I'm going to assume that they basically have a full rank for the schools that are relevant, okay? Another thing you can do is assume that non-ranked schools are worse than the outside options, so that you don't even prefer, so that you basically say, oh, I didn't rank this school, this is really, I prefer not to be assigned to anything rather than being assigned to a school that they didn't rank. Well, that would be problematic if you see people really exhausting the list, right? If really, so you can only rank 12 and people rank 12. So then you're, yeah, I mean, you didn't rank this other school, not because you hated it, it's mainly because you couldn't fit it in the list. But if you're in a setting where most people do not exhaust their full list, maybe this assumption is not so bad, right? So it depends on empirical context. Now, this is a paper that I was mentioning earlier by Factor and Letter He, where they say, look, even if you have a full report, if you're willing to assume that you are in you end up with a stable allocation, then you can go back and essentially apply the stability concept, the stability approach that I said before. So forget that you see the reports, just go back to stability and exploit the stability and use the formulation that we got for stability. Now, the key thing is that in this case, because you see the rank order list, you see the cutoffs. So you see the logarithm, so you can basically get the cutoffs back. Okay, so you can basically have the cutoffs and have stability. Okay. So okay, so those are all like easy fixes. So these are things that, okay, given a particular setting, I can make this assumption that, you know, I think is reasonable in my setting. And there's another approach that says, no, let's try to take this skipping behavior more seriously. Okay. So what do you think that you need to think about if you want to really take the skipping behavior really seriously, and you know that individuals should essentially sometimes skip schools that are hard to attain? What are the things that you need to also know or try to investigate if you want to really exploit that behavior? Can you do it with just the reports? What do you need to know?
Beliefs?
Yeah, exactly. You need to know. You need to have some notion of beliefs. Beliefs about what?
Probability that you get into a school.
Perfect. Yeah. You need to be able to say, look, yeah, these people are going to skip schools that are unattainable. That is, schools that they believe have a very low probability of getting into eventually, right? Good. So we need to basically try to come up with a way to estimate these beliefs. Yes.
Why can't I just take the rank order list and create inequality with, you know, the probability that A is better than B? If I rank A above B, I can say the probability that A is better than B is at least the probability that I see in the data.
Right.
Construct those. I don't get a like with me.
You will get a set of moment inequalities.
Yeah.
Yeah. So that's another approach. Yes. Yeah. Right. Exactly. Yeah.
That's hard because on Carlo.
They're going to be, yeah, exactly. So the question is, then you need to figure out, okay, which moments are you going to use? But if you have a sufficiently parsimonious parametric model, maybe you can get some. I mean, you don't need to use all the moments. You can use the sufficient moments to identify your model. So yeah, that's a very good. Yeah, that's another way to think about it. Yeah, yeah, exactly. Yeah, and yeah, I mean, there's things to be done in this area, and new ideas. As you see, all the papers that I'm citing here, it all is very recent. So it's very recent. So these are things that you can think hard and come up with clever solutions. Exactly. Okay, so there is one idea. Okay, that's exactly right. So you said, okay, I want to estimate these beliefs. So I want to see, okay, which are the popular schools? Maybe I can look at what are the schools that are ranked by by a lot of people, and those are schools that are going to be popular. And then I can say, okay, maybe I can. I'm going to say that, well, if I didn't rank a school that is not popular, that's because I don't like it. But if I rank a school that is popular, maybe I can't say anything, and maybe I can use some moment inequalities, or I can create some, or I can basically not construct my likelihood in a way that doesn't take that into consideration. That I just don't say anything about that school. Yeah. Okay. Good. So yes, question.
In this case, popularity is also endogenous.
Yes. Endogenous in what sense? Okay.
If everybody will not rank schools that are difficult to get, they might become unpopular.
Yeah, exactly. Yes. Yeah, no, right, exactly. In that case, we need to think about equilibrium concepts, right? And yeah, we're going there, right? So all I'm saying is that yes, we need to come with a way to figure out these probabilities, and that's what we're going to do next, essentially, after lunch, okay? But that's exactly right. We're going to be thinking about why is it that some schools are popular, some schools are not popular, and we're going to try to infer that from there. What do I learn about preferences, given that some schools are popular, some schools are not popular? That's exactly right. Okay, so yeah, let's have lunch. You see the recorder. If you know what you're done, yeah. Yes.
So I'm not going
We're gonna run.
All right, okay. I'm ready to start the second part of my lectures. So, yes.
I was wondering if you can explain again when you say using stability to estimate things, what exactly are you focused on, like stability out?
I mean both an assumption is that the observable location is stable, and as such, each individual is choosing the school that gives them the maximum linear utility among those schools that are in the budget set. In the budget set means that are schools for which they have a priority that is above the cut.
I see, so it's just an interpretation of the data you observe.
Yes, it's a weak interpretation of the data. It's an assumption that allows me to give a particular interpretation of the data, and in particular, it allows me to derive some reference, reveal reference situations. Yeah. Well, I'm invoking stability. What I'm really doing is I'm assuming that when I see somebody in this school, and I see that the budget set of this individual was this, then I can argue that this individual prefers the school that they are assigned to any of the schools in the budget. Yes.
So this would be violated if students would underestimate what's available for them, wouldn't it?
Okay, so good. You're thinking, okay, let's put more context to that. Suppose that we have a DA with restricted lists. Okay, that is what we have, what I have in the slides right now. Then, if I make the assumption of stability, okay, and they are not reporting all the full list, then yeah, I may get and as a result, maybe a resulting allocation is not stable, then I may get the wrong answer. Exactly. Yeah. Yeah. Any other question? Okay, so yeah. Oh, sorry.
All right. Now, no, good. Okay, so let's recap a little bit where we stopped. We were thinking about restricted list DAs, and we said that this mechanism may be manipulable. And can anybody explain why this mechanism may be manipulable? What are the opportunities for strategic behavior here? Why would you strategize if you can only report a short list? Yes.
You might actually report a lower ranked university and choose not to report the university that you prefer the most because you might think you won't get it.
Exactly. So the reason is that, yeah, this school, I like it, but I'm not going to get in, very low probability I get in. And if I rank it, even though I know I'm not going to get in, I can't rank the K plus first school that I like, not so much, but I can rank it because the mechanism doesn't allow me to do it. So I may prefer to say, okay, I'm not going to rank this very, very competitive school so that I can rank at the bottom of my list the next school that I think I have a higher chance of getting. Okay.
Just a question.
Yeah.
You know, I would think of it in terms of expected, you know, like I'd say, I rank Harvard first, but there's very low chance I'm going to get into Harvard. So I'm just going to say the expected value is low, and I'm going to rank it low because I'm figuring in my expected probability of being chosen.
Exactly. Yes.
But it sounds like you're anticipating that people have to do it assuming they would get in. So what would you rank the schools assuming you could get into all of them?
Right. Okay, good. So that's exactly right. Up to now, we said we're only going to make inferences, taking the ordinal preferences that they report to us as clear indication of the true ordinal preferences that they have.
Assuming you
assuming that you got in. But you're saying, no, wait, once we allow for uncertainty in what's going to happen to me if I rank this school, all of a sudden I need to change completely my framework. I need to be thinking about choice and uncertainty, right? And that's exactly where we're going now. That is going to exactly where we're going. Yeah. So that's exactly right. Okay, so now let's think another mechanism where what John said is also going to be super relevant, that we're going to have to be thinking about probabilities, and this is the immediate acceptance mechanism. Now, let me tell you how it works, although I trust that you already know. So that, again, people report the rank order list, and the mechanism first acts as if students first apply to the first school in their list. Now schools are going to take all the students that rank them first, are going to order them according to the priority, and are going to immediately admit applicants up to the point where their capacity is met. And the key word here is immediately, right? Before it was tentatively, right? You keep this and I'm going to compare the ones that I kept with the ones that apply to me in the next round. Here, no. They apply to me, I admit them, and I move on. Okay? If you were rejected, then you're going to apply to the highest school that has not rejected you, and then schools that have capacity left, that is, that have not assigned all their seats in the first step, are going to take the new applicants and again admit students up to the point that their capacity is met or that they run out of students. And then this process continues until every student has either been already accepted by a school or has been rejected by all the schools that they ranked. Okay. So now, what are the things, what do you think that you should or should not strategize in this mechanism? What are the considerations that you need to think about? Yes.
Again, because in case you don't get your top choice, the next school that you might get could be a very, very low rank school. So you might, rather than, you might choose not to report the first few schools to probably get your second or third or fourth choice.
Right. So suppose that I like school A, then school B. School A is very, very, very competitive. I think I'm not going to get in. Most likely I'm not going to get in. There's a small chance I will. School B, it is competitive, but not nearly as much. Moreover, I know that school B is going to be almost full after the first step. Okay. So what happens there? School B is going to be almost full after the first step. So if I rank school B first, I know that I'm going to get to school B with priority 1, because I think that school B is going to, that everybody that ranks school B first is going to be almost sufficient to meet the capacity. But if I rank it first, I'm going to be one of the ones that rank it first. So I'm going to get to school B with priority 1. Okay. If I rank school A first, then I have a very low probability of getting into school A. But by the time that my file gets to school B also has exhausted most of their seats. So I also have a low probability in school B. So now I need to think about, do I want to get into school B with probability close to 1, or do I want to risk it and get into school A with some low probability, get into school B with some low probability, and with a very large probability getting into my third, or even remaining unassigned? Because by the time that my file gets to my third choice, maybe there are no seats left in any of the schools that I like. Okay, so here you are making a choice in uncertainty, right? And we need to change the framework so that we can interpret reports to the mechanism as a decision in the context of choice and uncertainty. Okay, and that's what we're going to be doing. Now, though you might ask, yes, Harry.
Right. This may be unrelated, and if you want to, you can postpone it, but there are these systems where you're only allowed to apply to 1, and that's it.
Yeah.
How does that?
In that case, it happens that immediate acceptance is identical to DA, and it's a DA with a very restricted list. It's 1, and it has it has the same properties as immediate acceptance, essentially. Because then you really want to say, okay, you only have to apply to 1. You apply to school A, very low probability of getting in. You apply to school B, very high probability of getting in. So you need to think about, okay, do I want to get at my highest value school, but with a low probability, or do I want to get my intermediate level value school with bigger probability? And then we need to trade off probabilities versus valuations, and that's where we're going. Yeah.
My second question is in the lecture this morning where you weren't there, there was this group of people that never got any. Never got allocated. I mean, is that realistic in public schools? I mean, there's always going to be a school.
Yes. Yeah, no, that's true. So I tell you about the context that I've seen, and it is the case that there are some schools that at the very end are still have empty seats, So those are schools that are going to take everyone that wasn't assigned in any of their schools. Yes. Yeah. Now that's typically the case. And typically the typical case is that there are a few schools that are basically have zero cutoff, and they take anyone that was not assigned anywhere else. Yeah. Okay. So yeah, this mechanism is obviously not strategy proof, and so why would we ever use a mechanism like this? Well, obviously, when Boston was thinking from moving to immediate acceptance and to DA, obviously there were voices supporting the change, there were voices not supporting the change. And it was interesting to hear, to listen to what parents had to say when they were trying to prevent moving from immediate acceptance to DA. They say, well, if I understand the impact of Gale-Shapley, and I tried to study it, and I've met with BPS staff, what I understood is that in fact the random number has preferences over your choices. What this is saying is that now your report is not going to enter in your priority score, but the lottery number is going to enter in your priority score. So before what you chose had a lot of importance in determining your priority score for a school. Now it doesn't. So in a way, they were saying, look, it seems that now now this random thing is going to have preferences over my choices. Another parent said, I'm troubled that you're considering a system that takes away the little power that parents have to prioritize. What you call strategizing is a dirty word, okay? I mean, it's hard to put this in a context of an economic model, but we can try. And there's a very nice paper by Attila Abdulkaliloglu, Yonkuche, and Chesuda that says, okay, let's try to build a case where parents are right. So these two parents are right, because there were parents saying, oh yeah, it's great, Gale-Shapley is great, like everything, right? People pro and con. So, but okay, so let's think about this very stylized case. Suppose that students all agree that school A is better than school B is greater than school C is better than D, and so forth. So they all have the same ordinal preferences, okay? Suppose that school have, just to make it stark, schools have no priorities, okay? So schools are going to break ties using a random number. So this is an extreme case of the lottery has a lot of power over my allocation, right? So what's going to happen here? Okay, if you think about what DA is going to do, is basically everybody's going to, DA is strategy proof. Everybody's going to rank the exact same rank order list, right? They all prefer A to B, B to C. So everybody reports the same. Now the mechanism is going to say, oh, everybody reports the same. I'm going to randomly generate a lottery number. I'm going to generate a random allocation, essentially, right? So now we have a random allocation, and the random allocation is only due to the random lottery, not because some students had more priority than others, students had siblings, there were neighbors in the neighborhood, and so forth. This was just random. So you can think that we can improve over this random allocation. How would you try to? What are the sources that you, suppose that I tell you, well, this is allocation. How would you try to improve over the allocation that is random, essentially? What are the things that you could start doing to try to improve this allocation? We have a random allocation, so I mean, anything that we do could be a little bit better, right? So what are the things that you could start doing?
Open an aftermarket.
Open an aftermarket. So we say, okay, look, I got into this school. I know that the school that I got in is a school that you prefer, but really I like it a little bit more. I know that you just told me that you like it a lot. Maybe we can arrange a trade here, okay? So there are a lot of trades that don't happen in this case, right? And the main thing is that in this case, the DA, when you report ordinal preferences, has no way to take into account the intensity of preferences, because you only report a list that is your rank order list. There's no way for you to communicate how much you like a particular school, right? The mechanism doesn't have that language. So what they find is that, in fact, an immediate acceptance, Pareto dominates DA from an ex ante welfare. And why is that? This is because if you think that this is because it's starting to use ordinal preferences, cardinal preferences, right? The intensity preferences. So it also says that even if you have some people strategize, immediate acceptance may not harm, but rather benefit those who do not strategize. How come? Any intuition? Intuition is not that simple, but I want you to take a couple of minutes to think about it. Okay.
Strategizing guys leave the popular school and start to go to more school, start to go to less popular, and they less like, but they have more chance to go to. So the students who do not strategize still want to go to the most popular school, and their chance increase in that way.
Excellent. Yeah, exactly right. So let me say it aloud so the people online hears it. So suppose that we have, again, A preferred to B preferred to C by everybody. Now we have this group of people that strategize. So what does strategizing mean? In this case, it means that I'm going to rank B first instead of A. But what that means is that now less people are ranking A as a first choice. So people that didn't strategize and were naive, all of a sudden have a higher chance of getting into A, because some of the people that are now strategizing are saying, no, screw this, I'm going to rank B first. Okay? So you have that even people that do not strategize may benefit from this change. And they have another argument that even if you include priorities, IA, that is immediate acceptance, facilitate access to good schools for students with no priority. And this is again because now some students, even if they have priority, they may say, okay, you know what, I'm going to, some students that don't have priority in a particular school are going to basically say, okay, I'm going to not rank this school that is good, leaving more space for people that really like that school to rank it first. So there is some sorting that people self-select out of competitive schools by not ranking them first, okay? But the key thing is that here we really cooked up an example, right? We said, oh, everybody agrees that A is better than B, B is greater than C, C is greater than D. So in a way, we're building a particular example in which all those intuitions work. That tells us that maybe this is not a general result. And that tells us that estimating preferences is important to understand whether the benefits of one system over the other. Okay, so that's where we're going to go. We're going to basically build a framework that would allow us to estimate preferences when we have manipulable reports. Okay, any questions before I get into the nuts and bolts of the framework? Yes.
So if I the choice of the best mechanism depends on the underlying preferences of the population.
Yes.
So it might change year to year as well. So
say that again, sorry.
It might change every year as well. If preferences change over years, then the choice of mechanism.
Yeah, no, true. Yes, I agree with you. Typically, what we're going to think about, but that's a good question. Typically, what we're going to think about is that individual preferences are drawn from some distribution, and this distribution is evolves slowly, okay, if at all. Okay, so as I was talking to John, we need to change the framework. Now we're not going to interpret reports to the mechanism as a true revelation of the ordinal preferences of individuals. Rather, we need to think about choices under uncertainty. Okay, so now a report, when you say, oh, A, then B, then C, what you're really saying, what you're really choosing is a lottery. that is going to give you school A with some probability, school B with some other probability, and school C with some other probability. So now we can go back to essentially chapter 5, I think, of Mascolo, Wisdom, and Green, and try to think of, okay, let's put this into a framework of choice and uncertainty, okay? So each report, I can think of not only as a list of schools, but I also can think of it as giving me a vector of probabilities, so it's a lottery in the standard framework of choice and uncertainty, and now agents are going to have to form beliefs, as we talked yesterday, right? Beliefs about these lotteries, and they're going to use these beliefs to basically inform their choice and their uncertainty. So we're going to have different ways, there's several ways that you can think about forming these beliefs. One is rational expectations. So you think that, okay, I have an equilibrium, these individuals are have rational expectations. I'm going to try to figure out what would be the beliefs and rational expectations. You can also think, okay, I can think about maybe last year the mechanism was run and parents have access to some of the outcomes, and maybe they can construct the lotteries based on what happened last year. Or like in a paper by Adam Kapoor, Chris Nielsen, and Seth Zimmerman, published in the ER in 2018, you can go out and try to ask the parents, okay, what do you think the probability of you getting assigned to school is, if you rank it first, if you rank it second, and so forth, okay? But you need to come up with a way to basically form these beliefs, and I'm going to talk a little bit about that, but that's going to be a component of the analysis, okay? Now, suppose that somehow you came up with these beliefs about lotteries. What you need to think about is, okay, what do I learn when I see somebody submitting a particular rank order list? Okay, what I learned from that is that the expected value of that lottery, so the expected utility implied by that lottery, is greater than the expected utility implied by any other lottery that I could have submitted. Okay, so we go back to Mascolo, Wisdom, and Green, and we say, okay, choice and uncertainty, each of the possible outcomes has a particular utility. Okay. Yeah, that had an impact. Yeah. So good. So every outcome has an outcome, every outcome has a utility, and then my expected utility is just the probability weighted average of my of the individual outcomes utility, right? So notice I'm not making any assumption about risk aversion or anything. These are individual outcomes. If the axioms about choice and uncertainty are satisfied, these are my revealed preferences relationships. Okay, so notice that I have V on both sides, so I can basically subtract one to the other side, and I'm going to say that V rationalizes a particular choice of a report, V rationalizes a particular choice of a report, if V is such that V times the difference between LRI and any other LR is greater than 0, right? Because I moved this to the other side, that's a difference. So I have V times the difference of lotteries greater than 0. So now I'm going to have one of these inequalities for each possible report that I could have submitted, okay? Notice that what I have therefore is each of these reports gives me a half plane, sorry, a half space. So I have a intersection of all these half spaces. What I end up with is with a cone, okay? A cone in utility space. Okay, so if I have two schools, school 1, school 2, and I have, say, 3 reports that I could submit R prime and R2 prime, I'm going to have 3 cones that are going to indicate which report I should submit if my utility falls in, depending on where my utility falls. Okay? Now these cones don't have to coincide with the orthants or with the 45-degree line because these are differences in lotteries. So these are a little bit more free than before. Okay, but in principle, if I have 3 schools, I can rank, say, school 1, school 2, school 1 and 2, so forth, and these are going to give me different reports, and then I'm going to be able to, once I have the lotteries, I'm going to be able to construct this map. Okay, and now what I'm going to say is, okay, if I see somebody reporting R, then I know that the utility is going, the inner utility fell within this cone. So, okay, good. So what is not so good about this anymore? One thing that we liked about our logic models was that they give us closed form solutions. And part of the reason that they were giving us closed form solutions is because we were integrating over these nice, well-behaved regions that basically coincided with the orthons and the 45-degree line and taking the max and so forth. Now we lost all of that. Okay, so we need to come up with a way to estimate these models that can accommodate integration regions of the likelihood that have these funny shapes. Okay. Okay, so now, as I say there, logic models lose their appeal. Even if I say, okay, let's do probits, still integrating normal over these funny regions is not an easy task. In particular, when you have more than two schools. So we need to come up with something different. Okay. And that is when you realize that actually you can rely on Bayesian methods. Okay. Why? Well, because we need to avoid computing the likelihood. So we would like to basically run an MLE without actually computing the likelihood at any point. And we see that people in the marketing literature or in economics have been using these machine Bayesian methods that typically they use it in the context of discrete choice where the benefits over logics are not so great. But here we're going to see that the benefits are going to be substantial because they can be adapted to estimating models where you're choosing over lotteries rather than choosing over particular over products. Okay, so let me give you a very fast introduction to these Bayesian methods. So first, remember your frequentist approach. If you want to write the likelihood of a parameter given the data, that is defined as the log of the density of the data given the parameters, right? That is what the frequentist would do. Now, theta is really a parameter. It's not data. It's not a random variable. It's a parameter. It's fixed, and the maximum likelihood estimator is basically theta that maximizes the log likelihood. Okay, and you saw in Whitney's lecture that under regularity conditions we can show that the MLE estimator is consistent and asymptotically normal. Great. Okay, so that's the approach. Now, in the Bayesian approach, we say no. We're going to think of theta as a random vector of now not a parameter is a random vector of random variable essentially, right? Now, the distribution of theta, the random vector theta, given the data, is going to follow the Bayesian rule. Okay, it's going to be equal to the distribution of the data given the parameter times the density of the distribution of parameters divided by the density of the data, the margin of the data. Okay, so what is f of theta that I have in the slides? Well, that is every prior information that you have about the behavior of theta. So that is your prior. Okay, so anything that you know from theta before, you codify it in this f of theta. Now, f of theta, right, the density of the data is just the integration of the density of the data condition on the parameter over the distribution over the distribution of theta of the prior. Okay, so we know that. So if we could come up with a way to get this f theta given data, we would have all the information that we want about the parameter theta given the new data. So that's a posterior distribution. And if we know the posterior, then that summarizes everything we know about theta. So we can compute the distribution, the synthetic the distribution, and so forth. And moreover, we have that there is a result, a series of results, the Bernstein and von Mises theorems, that essentially say that under sufficient some conditions, irrespective of the prior that you have on theta, you are going to end up that the posterior is a Gaussian. Okay. Sorry. The posterior is Gaussian, and then you are going to have that the mode of the posterior is going to be is going to converge to the MLE estimator, right? So good. So this is what we're trying to do. And the key thing is, okay, you say, well, I'm super excited about this, but then I'm a little bit, again, not so excited about it anymore because this depends on this f data of theta that is essentially the same thing that I have here. And then like, okay, well, I'm back in square one. But wait a minute. We're going to keep pushing here, okay? But okay, so I understand that the problem is with this f data of theta. It's the same thing that I had here, so I need to figure out a way. Okay, so suppose that I can't compute that. Suppose that I can't compute that, but suppose that I could sample from it. Okay, if I could sample from it, I could essentially sample a lot and then basically estimate the distribution. Okay, so I need to find a way to sample from a distribution, even if I can't compute a closed form for it. Okay. Again, I mean, it's hard to sample from a distribution that you don't know, that you can have it, that you can put your hands on, but this is the trick. Suppose that I can divide theta into sub vectors, essentially, theta 1 and theta 2. And suppose that f of theta 1 given theta 2 on the data has a closed form. And suppose that f2 given f theta 1 given the data has also closed form, and I know how they work. Then I can construct a Markov Monte Carlo chain. How would I do that? Well, I would start with some arbitrary theta 1. I'm going to note O is 0 because it's my first guess. Then I'm going to sample theta 2 from the distribution of theta 2 given theta 1. And then I'm going to, again, that's going to be my, say, theta 1. Okay, this is going to be, sorry, theta 2, 0. And then I'm going to do the same thing, but now I'm going to get theta 1, 1, that is my next, that is a new theta 1, by sampling from f theta 1 given theta 2, my previous one. So I iterate one, I go the other one, and the other one, and the other one, and the other. Okay? Actually, this algorithm is called give sampler. Okay, when I can do that. And when I have nice distributions for f that I can sample from. There are other algorithms that also generate Markov Monte Carlo chains. For example, Metropolis Hastings, Hamiltonian Monte Carlo. There are different ways to sample from distributions when you don't have a closed form solution, but you have some of these, some additional properties. Okay. Now the key thing is that if you do this for long enough time, then essentially eventually the theta k that you get is going to be, for theta k large, is going to be essentially a random draw from the joint distribution of theta given the data. That's the beauty of it. So even if I can't get my hands on f, I can't get a closed form for f, and I can't sample from it. If I can break down the posteriors of theta 1 and the posterior of theta given theta 2 and the posterior of theta 2 given theta 1 in a way that have closed form solutions, I'll be back in business. That's the key thing. Okay? Any questions on this? I'm going to tell you exactly how it works for a school choice now, but I want you to get the high level idea. I know it's very crash course in Bayesian, but it's a bit hard, but I want to get the main idea. Okay, so let's think about going back to school choice. Okay, so I'm going to say that the value, the indirect utility of student I for school J is equal to a vector of characteristics x times a coefficient beta minus a numerator dij. You can think of tuition or distance, and then I'm going to have a shock. This shock is going to be normal. Okay. why normal? Because I want to get distributions that I can sample from and have nice closed form solutions. So all this assumption is because I want to eventually use my Gibbs sampler. Now beta is now has a prior that has a mean of beta a bar and a particular variance. If you want to say, look, I want to be very agnostic about beta, I don't want to bring a lot of prior information, well, then that means that you don't know much. That means that your sigma is large. You have a very dispersed prior. And then we're going to say that sigma, that is the variance of epsilon, is distributed from an inverse Wishart. Okay, probably you've never heard of what a Wishart distribution is. What you need to know is that it works for this case. It's just a distribution that has very nice posteriors, because what we are going to try to do is draw from posteriors that we already know. In a way, once you read about it, it sort of makes sense how it works. It's not so esoteric, but yeah, I mean, the first time that I encountered it, I was like, wow, this is very esoteric. But in fact, it's not so much. It's just think about accumulating the elements of X transpose X matrix that you keep accumulating, and you know that all of these elements are going to convert. The average of those elements are going to converge to something. So if you accumulated this many, you can keep accumulating if you have the new information. So it's a way to aggregate that information as you have more and more observations of a vector of random variables. What is the dispersion they have? Okay, so just do that. Okay, so now there's going to be an extra trick. That is data. Yes.
So I'm not sure here. Before, when you named the von Mises-Bernstein theorem, was that a statement about the distribution of the mean of a given parameter or of the parameter? Because since we're based
No. The von Mises-Bernstein, the theorem about the distribution of the posterior, that it eventually becomes under some conditions.
Yeah. Okay. So it's it's over the posterior and not just the mean of the.
No. And an implication of that is that the mode is going to converge to something. Okay, no, that's right. Another result is that on top of that, the mode of the posterior is going to converge to the maximum likelihood estimate. So there are several types of ones.
Now when you have you sample the what is called the covariance,
Yes.
it cannot it's not normal in the traditional sense because it cannot have negative values, right? For example.
Well, but it's going to become the posterior is going to become very close to normal, essentially.
Okay,
Because essentially it averages over these products of elements, yeah. I see what you mean. Yes, right. Yeah. So for this parameter, the posterior is not going to be normal because, as you said, there may be zeros in the variance covariance matrix, and you can't get a zero. Yeah. Okay. So good. Yes. So what we're going to do is data augmentation. Essentially, what data augmentation means is that now we're going to think that these indirect utilities that we don't see, we're going to basically add them to the vector parameters. So now theta is going to include V, sigma, and beta. Question?
The plus of this approach is it to be able to estimate correlation between error terms?
Yes.
For example, if I had assumed error terms are independent and normal 0, 1, but instead estimated for scale, estimated the coefficient for distance. I could have done that, but I wouldn't be able to get a correlation between error terms. Is that right?
Correct. Yes. So if you put a coefficient on D, all of a sudden you need to make a normalization on sigma, because otherwise you can multiply everything by a constant. And in that case, it doesn't fit this framework anymore because we don't know how to impose constraints on sigma in the Bayesian framework. So that is why we did it this way, where we normalize one coefficient instead of normalizing the variances. Yeah, you're right. Like, yeah, that's right. All right. Okay. So good. So okay. So now suppose that we have theta composed by those three elements: V, sigma, and beta. Okay. Okay. Let's think about this. Suppose that I see sigma and I see V. Suppose that those are given to me. Then essentially beta is just the parameter of a regression of V on X, okay, and with some errors that have some variance that I know. Okay? So beta is essentially can be obtained from a regression. Okay. Well, this is going to be a Bayesian regression essentially, but it's going to be a regression, and we know that regression coefficients tend to behave as normal by the central limit theorem. But even in the Bayesian framework, if we assume that everything is normal, the betas are going to be actually normal. Okay, so beta given sigma and V has a normal distribution. The vector has a normal distribution. Now, suppose that I fix beta and V, essentially the errors are, I can compute the errors, and I can compute the correlation between the errors, and I can compute a correlation matrix. And I was telling you that the wizard accumulates, well, the information about basically correlations. So sigma given beta and given V is going to have an inverse wizard procedure. Okay, and this is the whole reason why I assume that this was inverse wizard, is so that I can assume that I can get that the procedure is going to be the inverse wizard. Now, what I'm going to try to convince you is that I can basically compute V given the other values of V, betas, sigmas, and the cone that you chose as coming from a truncated normal posterior. And this is going to be the key thing that is going to make this whole system work, that now I have a way to do this data augmentation and stay within the parametric forms that I want to stay. Okay. So that's what I'm going. That is what I'm going to do. So in particular, I'm going to initialize sigma 0, V 0, making sure that I initialize the value for each individual in the corresponding cone that matches the report. And then for every k, I'm going to draw beta given sigma and V from its normal posterior. I'm going to draw sigma from conditional on B and K from its normal posterior, from its inverse wizard posterior. That's a typo here, inverse wizard posterior. And this is essentially a Bayesian regression of V plus D on the x's, computing the betas and the variance and covariance matrices. In fact, it's a Bayesian system of seemingly unrelated regressions, because I have several equations, one for each school. Okay. And then the last thing that I want to do is update V given the other values of beta and sigma. Now, notice that when I update, this is here, in step k plus 1, in step k, I'm going to update beta to this beta k plus 1 value. And then when I update sigma, I have beta k plus 1. So every time I'm updating, I'm always updating. It's not that, one coding mistake would be to basically write beta k here. Should be beta k plus 1. And again, here, I'm going to draw vk plus 1 given the new draws of beta and sigma. Yes?
So when you say that I0 belongs to the cone,
yes.
How do you get the cone? You need to have some assumption of the.
Yes. Remember, what I said here is that we can talk more later, but I'm assuming that you came up with some way to estimate these lotteries. It can be because you assume rational expectation. It can be because you basically estimated from last year, or it can be because you went and asked them. You elicited some preferences. Sorry?
This is an input to the model.
Yes, that's an input to your model. Yes, exactly. Exactly. Yes. And once I have the lotteries, I can construct the cones, because the cones are basically the V's that belong to this intersection of half spaces, and each has, right, and that defines a cone, because you have each evaluation between one report to the next gives you like a plane that divides the space of utilities in two. So you have, then you need to do it again, and so you're going to have this intersection, and it's going to essentially be a cone. Right?
Just to make one connection.
Yeah.
So these lotteries using the data from the mechanism can be constructed like the probabilities that Irene was constructing using her cutoff function. You take the cutoffs and you look at the probability that you're about to cut off each thing, and vary the rank order list and see where you'd be assigned, just like Irene was doing.
Yeah, I'm going to talk about that. Yeah, but that's exactly right. That's exactly right. I'm going to basically say one way to do it. Yeah. Exactly. Yeah. No. That's exactly right. Yeah. Good question. So yeah. Okay. So now what I need to tell you is how on earth I update these V's. Right. That's a whole thing. That's a whole new thing here, because this step and this step, these are standard in discrete choice cases. People do it all the time. The key thing is how to update these V's. Okay, so remember, suppose that I start, this is my starting value. I initialized V here, or this is the V that I got in step K, right? This is a point in the cone, so it's okay. This is V1 and V2, it's in this point, okay? So the first thing that I'm going to do is I'm going to say, okay, given V1K, that is this value of V1K, and given beta and given sigma, V2 is normal. But in order to be in the cone, it has to be bounded below by this value over here, and bounded above by some value at which this dotted line intersects this ray. Okay, that is going to ensure that the condition on V1, I draw V2 and I stay in the cone. Okay, so everything is going to be normal. Why? Well, because the V's are normal. Everything is normal. The V's of other schools are normal. So I can take the conditional distribution of V of one school given the full vector of V's of other schools. Okay. Good. So I'm going to draw a new value. So suppose that I do this and I draw a new value and I get this value. I get this V. So I drew this particular value of V2 is on the same line as V1 because I only updated V2. Now I can do the same thing. I can now, given this value of V2, I can draw V1 given the beta and given sigma, again from a truncated normal. The lower bound is given by this point over here, and the upper bound is whenever this line crosses this ray. Okay. So I'm going to get a new draw, and that is going to be my new draw. And it's in the cone, because I always stayed in the cone. Okay. And that is why you can update V, and that is how you can run this chain for very long. And if you let it run for a couple million times, you are going to get draws that are draws from the procedure. Yes.
How do you update the V's for choices that aren't ranked by the students?
Good. Remember now, a cone is associated with a report. I don't need to even tell you what the report says. As long as the set of reports partitions the space in sufficiently well-behaved cones, I'm fine. In particular, it's going to be, so not ranking a particular school is not a problem, but in fact, what's going to happen in that case is that you're going to say, well, you prefer school 1 to this vector, this report to this other report. If you didn't rank school, say one particular school, you're going to have a probability of 0 of that school, of you being assigned to that school given your report. But you could have ranked another school, you could have ranked that school in a different report, in which case you would have a positive probability for being assigned to that school, in which case the difference between lotteries is going to give a negative number. And that's fine. There's no remember that this race, going back to the question. So remember that these L's are differences between the assignment probabilities here of the rank that you chose versus any other rank. So rank order list. So for some of the rank order lists that you rank the school that you didn't rank here, this is going to be a positive number. The difference is going to be a negative number, and you're going to have another half space. So there is no issue with schools that you rank or you don't rank. There is a little bit of an issue with schools that you have no chance of getting whatsoever. Because if you have a school that you have no chance of getting whatsoever, then L is 0, L for that component is 0 anyways, in any report. So that is an issue, and yeah, that means that in that case, your code is not going to be what is called pointed. It's going to contain a subspace. It's going to contain line, but it doesn't matter. The whole, as long as it doesn't matter in principle.
So does this also work then with like choice sets that are large? Because this only works with choice sets that are small. There's an application.
Okay, yeah, this can blow up if you have way too many schools, because you have way too many rank orders possible. Yeah, that can become a problem. So yeah, exactly. So suppose that you can run. Suppose that you have in the mechanism proposed by Harry that you can only rank 1. Then assign the number of rank orders is equal to the number of schools, and you're fine. If you can rank 2, assign is okay. Choose 2 out of okay. If you can rank 7, well, then it starts being a little bit too much. Yeah. Yes.
I think I'm asking the same question again. This method depends a lot on probably getting the correct expectations. For example, let's take adaptive expectation. What if this for example, the IA mechanism has been going on for a long amount of time, and there are some schools that are 0 because you don't think you'll ever get it, and there are some schools that are 0 because nobody likes it.
No, wait, those are 2 different things, right? No, sorry. I liked everything that you were saying up to that point. So what is 0 here? Because I think you changed the zeros.
So in the likelihood of getting, the probability of getting to that school, because it's not been like the way you derived this expectation had problems.
Okay. So let's define what probability we're talking about. What I'm saying here is that if you choose a particular rank order list, conditionally you choosing this particular rank order list, it implies a particular set of probabilities over you being assigned to different schools, right? Okay, so those are the lotteries. The fact that, so if nobody likes this school and you rank it, then probably the likelihood that the probability that you're going to get into that school is going to be high. So it's not going to be 0. That is why I wanted to stop you there, because, but you're right that if this school is very hard to get in because everybody ranks it first and so forth, and I don't have priority, then it's going to be 0. Yes.
Regarding this blowing up, if there's many choices, we can for each person restrict the number of choices, say like the 5 closest school, right? Even though we have 30 or 100 potential schools, that would be possible, right?
I have to think about it. Yeah, you're saying, is there a way to really coarsen these sets and still be in game?
Yeah, so say if we had a large school district, like, we
Yeah.
didn't need to, like 200 miles away, like just discard them.
I don't know. I'll have to think about it.
I should also point out there are 2 papers last year on the job market that made a small modification
Yeah.
on this model to try and make it much more computationally trackable.
Yeah.
By Edu and by Juan.
Yeah, but it is a open question of, okay, this, yeah. I mean, for showing what I'm going to be saying in the next 4 or 5 slides, we used this in the context of Cambridge. We had 13 schools and you could rank 3. So choose 3 out of 13 is not a small number, but it's not an astronomical number. It's something like well, we had some other constraints that basically made it that we were thinking about on the order of 2,000 possible reports per student. Okay, so good. Where was I? Going back to, but I love these questions. Keep them coming. Okay, so now I'm going to get into what Nikhil and I did in our 2018 paper. So this is right here, Cambridge. Cambridge used the Cambridge mechanism, but it's really an immediate acceptance mechanism. And roughly we could figure out that there were 2 sets of schools, some that were very competitive and were almost always clearing in the first round. So if you ranked them second, you were out of the game, mainly. And non-competitive schools that basically tended to have spare capacity at the end of the mechanism. So either there were schools that if you didn't rank it first, you wouldn't get in, or schools that you could get in no matter where you ranked them. Essentially. I mean, it didn't have to be that way. It just happened that was the way that the Cambridge was set up. Right? So that gives incentives to pick the top rank very carefully, right? Because there you can choose a school that is non-competitive that you like, is close to you and is, you know, your teachers and so forth, but it's not very competitive, and you're going to get for sure first if you rank it first. Or you could basically try to go for one of the competitive ones. Okay. Well, if you're in this case, if you are choosing between a competitive and a non-competitive one, if your second one is non-competitive, then probably you want to rank the competitive school first, because okay, I get it. If I get to a school, great. If I don't get it, I get into my safety school that I'm going to get there for sure. Now the question is, what happens if you have your first and second choices? Your first and second preferred schools are both competitive. Then you might say, okay, I want to think about my priority for the schools. Maybe I like the priority for which I don't have the school for which I don't have priority. Maybe I like it that a little bit less, but I have priority in that one. So my chances of getting in are much higher than in the other school. So it's going to be very important to pick your the top rank very carefully. So now let me try to provide you with some evidence that people were in fact making strategic choices, and then we're going to apply our method to estimate the preference. Okay. Okay. So one thing that Cambridge has, I guess, is that you get priority to the 2 schools that are closest to where you live. Okay. So that means that if you're choosing between a school that has priority, in which you have priority, versus a school that you don't have priority, you might, the probabilities of getting, and they are both competitive, the probability of getting accepted in the school that you have priority is much higher than the one that you don't have priority, because you're going to get processed before all the people with a priority, whereas in the other one, you're going to get processed after all the seats have been taken with people with priorities. Okay, so if you have 2 schools that are competitive that you prefer, and one you have priority, and in the other one you don't, for the reasons of probability of acceptance, you should be more likely to rank the one where you have higher priority. Okay. So what we did is essentially, so here, let me show you this. What we did is essentially say, okay, suppose that in the map of Cambridge, we construct a boundary that basically at each point in the boundary, at one side of the boundary, you have priority on a particular set of schools, and on the other side of the boundary, you have priorities on a different set of schools. Okay, we can create those boundaries by looking at the map and by computing distances. And we're going to compare people that were on one side of the boundary versus people that were on the other side of the boundary. And we're going to ask whether one of the schools that was ranked first was a school that you had, sorry, an observation here is a school and an individual, and we're going to ask whether that individual ranked that school first. Okay, and what you see is that at the boundary there is a discontinuity jump. People on the left on the boundary are much more likely to rank the school first because they have priority. People on the other side of the boundary have less of a probability of ranking that school first, and that is because they don't have priority. And this is a piece of evidence that people seem to be discontinuously reacting to the change in priority. Now you may say, well, maybe this is because people really like schools that are closer, and they just compare and look at the school that is closer, and they just rank those. Okay, then we said, okay, suppose that I construct placebo boundaries. That is, I construct the boundaries as if Cambridge gave priority only to people, gave you priority only to your closest school. Okay, so those are going to be different boundaries because they're going to be boundaries around each particular school. And if we do the same analysis, we don't see any discontinuity. Okay, so it seems to be that, and we did it with the three, and it also didn't work. We also did it with looking at schools that were competitive versus no, and all the effect is coming through competitive schools. Okay, so that is evidence that that is evidence that in fact people were responding to these priorities. Okay. Okay, so as I was telling you, there were 13 schools. We have 5 years of data. There were 13 schools, and this is why you choose 3. So 3 out of 13 is not so bad. There were a bunch of constraints about programs having language, schools having language programs, and there was some restrictions that if you spoke Spanish at home, you could apply to amigos with the bilingual system, and if you don't, you couldn't. But so there were a bunch of restrictions like that. But just want to show you that the closest school to a student was at about half a mile, just to give you an idea when we compare magnitudes. But the average school in the whole Cambridge has almost 5 miles from east to west, was about 2 miles. Okay. Okay, so now the question before was, how is it that we can construct the lotteries, right? And that was an important building block to all everything that we did. We said, oh, these lotteries are going to be input to the estimation method. We need to have them somewhere. I tell you how we did it if you want to assume rational expectation, and how we can do it if you want to assume adaptive expectations and so forth. So in Cambridge, they had the single tiebreaker rule. So each student gets a single tiebreaker that is going to determine the priorities in every school. And okay, the immediate acceptance mechanism has a cutoff representation. Okay. So if you want to estimate the rational expectation lottery associated to each report, one thing that you can do is go ahead and resample with replacement n-1 individuals from your sample, right? So you're going to resample that. you're going to run immediate acceptance, right? You are going to run a new lottery for each of the other students, okay? And then you can construct, you can add this particular student that reported R to the data set, construct the market clean cutoff, okay? And ask yourself, okay, did the priority of this individual clear the threshold for each particular school, and where would this individual have been placed for different values of nu? Okay, so you can see for each value of nu, where would this individual be allocated? Okay, for each draw of the competitors' reports. So then, for each draw of my competitor reports, I can construct the probability that this individual is going to be placed in the different schools that they rank. Why this is a probability? Well, because it is the individual lottery number, is a single tiebreaker that is going to say, well, if your lottery is very low, you're going probably not to get to your first few choices because your lottery was low. As the lottery gets larger, for this particular realization of reports, you may get your second choice or even your first choice. And then we can average that over different draws of competitors' reports and priorities. And that gives us a set of lotteries that we show that as the number of students grows large, and if we allow the capacity of schools to also grow with the number of students, so this is a synthetic result, this estimation of the lotteries are consistent for are consistent, meaning they're going to converge to a particular lottery vector that is the equilibrium of the limit game. So this continuous market economy that Irene was talking about, well, we use that to say, well, actually these lotteries are going to convert. If everything is sufficiently large, we're going to be pretty damn close to that particular lottery vector. Okay. We also did something easier you can do is you can actually go and see the cutoffs last year. This is even easier. If you want to do adaptive expectations, you can look at the cutoff last year and figure out, okay, what lottery number I need in order to get to each school given the cutoff of last year. That's even easier. Okay, we don't need to resample for that. We just need to just look at the cutoffs last year. Okay, and different lottery numbers are going to give us a different location. Okay, any questions about that?
So,
yeah.
I don't know if this makes sense, but is there any scenario when we want to use like these methods in, like, say, a strategy proof mechanism? Like, for example, I don't know if people are not understanding that the mechanism is strategy proof, and they are trying to use certain probabilities or some way.
Yeah, I mean, if you have evidence that people are doing that, and you have a behavioral model of like a model that basically says, oh, this is how people are behaving, yes, because even if you can use this idea, exactly. Maybe your revealed preference arguments are not going to be revealed preference arguments that you derive under choice under uncertainty of expected utility maximizers. It would be you have a different behavioral assumption. Yes, in principle, you could go and do that. Okay, so good. So good. So let me tell you a little what we found. We found that if you aggregate over everybody, going from the fair acceptance to Cambridge, going from the Cambridge to the fair acceptance mechanism is going to reduce aggregate welfare, but just not by a big deal, by 0.07 miles. So remember, closest school was about 0.6 miles. So this is a 1/10 of the distance to your closest school, more or less. And actually, the ones that the free lunch students don't benefit or lose that much, but paid lunch students that are essentially richer households because they pay their lunch. Free lunch students are students that apply to so that they get their lunch free, and you have to show that your income is below a particular threshold. So richer students are the ones that lose, essentially. And it's interesting to understand why is it that we find this. Well, we find that, not surprisingly, rich competitive schools are close to where rich parents live. And poor kids were basically not going to those schools anyways because they were basically living in the areas where the non-competitive schools were. And as a result, basically the strategic environment for poor kids was very simple. They could just rank whatever they wanted. They also prefer schools that are close by. So essentially for them, going from DA to Cambridge doesn't change much because they were basically getting the first choice anyways, as we see here. 87% of them are getting their first choice under Cambridge, and under deferred acceptance, and 88 in Cambridge. So nothing changes from them. But all the action happens with these guys, with the rich kids, well, richer kids, I guess. And we see that the model, the deferred acceptance, basically relative to Cambridge, assigns fewer people to their top choice. Okay, and this is to a true first choice, and the reason is that well, the key thing that is going on here is that parents that are the DA don't allow parents to express their cardinal preferences. Okay, so now what we have with Cambridge is that well, if you don't like a particular school, I mean, you like the school that is competitive, but you don't like it as much, so you don't rank it. So you go to the next next school. And things change a little bit when you think about courser beliefs or adaptive expectations. So things are changing a little bit here. The numbers are not so big as they were before, but they are on the same ballpark. So this gives us an idea that, yeah, I mean, you can question our assumption on beliefs, but if you change, you're not going to get much difference. Okay, so let me recap. I told you how to estimate preferences in a school choice context. We have a general model of student preferences, and the approach that we have depends on the mechanism and the availability of the data. Oh, so I have until 4:55. So I was rushing. Sorry, I was rushing without. So let me go back here. Good. So, any questions about this? The key thing here is that we estimated the model and the 4 assumptions. One is that suppose that you assume that people report truthfully and you forget about the fact that they are strategizing. That's this column. Okay. This is what if you apply your method, that is, people have rational expectations. And then we have another, this is what if, oh, sorry. This is what if people have adaptive expectations, that is, they use last period's cutoffs. And course beliefs, let me not talk about this for the moment. Okay, so the key thing to note here is that if you assume that people are reporting truthfully, obviously you're going to think that the Cambridge mechanism assigns a lot of people to their first choices because people are telling you the truth, and you assume that people are telling you the truth, and the Cambridge mechanism is trying to put people in their first choices actively because they are trying to maximize that. Okay. So if you for that, you're going to think that 79% of the people get assigned to their top choice. Now, if you look at what happens when we estimate the model and the rational expectations, well, in fact, this number is much lower because there are some people, you see the difference between the 79 and the 72 that are basically being assigned to the first choice that they reported that is not their first true choice because they are basically strategizing, right? Good. And in the Cambridge mechanism, you're going to see that now what more people are assigned to a second choice. Why? Well, because these are the people who rank the school that they prefer second first. Okay, and now the immediate acceptance mechanism is rewarding them for that and placing them in the school that they prefer the second, right? Because these are people that say, oh yeah, I'm going to go for the safe option in the second one. And notice that most of the action is happening in the paid lunch kits, right? Paid lunch kits, I have the number of students that seem to be strategizing is much higher. If I compare these numbers for the free lunch kits, it's almost the same. This is why I was telling you that the strategic environment for poor kids was more relaxed. But for rich kids, you see it here that the number of people assigned to a second choice goes up from 6% to 18%. And that is what is driving the gain in their utility. That now by strategizing, they can essentially attain their second choice, whereas before they would have basically fallen through the cracks. And here we also have the number of students that would prefer DA to Cambridge, and the number of students that would be indifferent, and the number of students that would prefer Cambridge to DA. And what you see is that the number of people that have a strong preference for Cambridge is larger than the number of people that have strong preferences for DA. And this is again because the people that Cambridge is benefiting is people that have extreme cardinal utilities, people that have a lot of intensity of preferences for a particular school. Okay. And when we do everything with adaptive expectations, the results are similar, but are less extreme in terms of the magnitudes are a bit smaller, which says that probably that in fact, I mean, there's some robustness to the results. Okay. So again, I show you how to estimate a preference in school choice context. We define a general model of student preferences, and the approach basically depends on the mechanism and the data that you have available. We covered what happens when you have data on final stable allocations. We also covered what happens when you have data on truthful rank order lists. That is when you have data from DA, say, and report truthfully, and when you have data on strategic rank order lists, and that is the thing that we did after lunch. The findings that this literature has is that, well, in the case of Alonso Bucaray, that free tuition may have regressive effects that are not obvious at first hand. There are big welfare effects from centralized mechanisms in school choice. That immediate acceptance can increase the aggregate welfare, but that is only if students strategize correctly. But the difference between the mechanisms is smaller if the beliefs are biased. So this is the difference between adaptive expectations and rational expectations. But moreover, there are similar results that people have found in Barcelona. So there's a paper by Casamiglia, Well, and Fu, and they find similar results in the context of Barcelona. But there is another paper by Adam Kapoor, Nielsen, and Zimmerman. They say, look, if in a mechanism where people have wrong beliefs and they strategize incorrectly, so they make mistakes strategizing, actually the immediate acceptance can do very bad. Okay, and so they have a thing where look, they go and ask people about their expectations, and so that if you take their expectation, what they report at face value, they are making mistakes when making reports. Okay, so there are a bunch of exciting avenues for research. Nikhil is going to, and Parag are going to talk about mechanisms and outcomes. There are some papers about school choice and educational outcomes, papers by Attila Abdulkariroglu, Josh Angrist, and Shusuke Narita, sorry. And paper and Parag, paper by Pathak, Attila, Schellenberg, and Walters in 2012, where they also look at school choice and how outcomes change and where people tend to choose schools that are good for them. There are papers about the effect of affirmative action policies. There's a recent paper by Otero, Barona, and Dobbin. It's a job market paper this year. There are papers about informational interventions where you tell students about the programs and about the characteristics of the programs, and you evaluate how they make choices afterwards. This is a paper by Allende, Gallego, and Nielsen, 2019. And also, you can think about augmenting models of demand for schools with a model of supply, where schools decide to enter, to have some, to include some programs, some extracurricular activities, and so forth, and see how that affects demand and where that is something that the parents would value, for example. Any questions other than that? Yeah. Yes.
So your counterfactual is to look at the change in mechanism. But could you use your framework to, for example, change the supply of quotas, how that affects the beliefs about what you've been admitted to school?
Yeah, well, one thing that is ready you could do with any of these approaches is to say, okay, what is the marginal value of a seat in any of the schools in the district, right? In terms of the utility that will generate. That is something you could get right off the bat. By basically saying, okay, so what if I augment my capacity by 1 in this school, in that school, in that school, and see what is the total effect on welfare. You can totally do that. Now, you can also think about, okay, see in the data, what happens if one school expands capacity, how fast people adjust their expectations about
yeah, let's get it easy.
Yeah.
Right?
Yeah.
What type of expectations? I guess with the adaptive expectations, you not see that bigger.
Exactly. Or you would see it in a particular way. It's going to adjust in a particular way. Yeah.
But going back to your lecture yesterday, one thing that's not fully worked out yet in this literature is solving for equilibrium. And so the counterfactual that Paulo showed was to deferred acceptance. And because deferred acceptance is strategy proof, it's easy to solve for what people would say.
Yeah.
Now, if you had a counterfactual, which was a manipulable mechanism, you have to take some of the, you have to start thinking about how do I get the equilibrium lottery? So how do I get the equilibrium cutoffs, etc. The cutoff structure gives some structure to it that makes it more
but we don't know how to do that.
So
yeah, that was a limitation in counterfactuals when we were thinking about the counterfactuals. We say, okay, let's think about counterfactuals that we know how to solve, and when we were thinking about like changing the rules of Cambridge, we basically say, okay, we will have to establish an algorithm to compute the equilibrium of the Bayesian gain implied by this manipulable mechanism, which can be complicated. Any other questions? Yes.
Well, I don't know much about the system of Cambridge, but what happens if students do not match with elementary schools in the system?
Students? Sorry?
Do not match with schools. What happens if students do not match with schools?
do not match.
In Cambridge? Oh, well, they're going to go back to one, they're going to get into one of these non-competitive schools. Eventually, if after your if you don't get matched, well, okay, yeah. What happens is that you get placed into one of the non-competitive schools, but in reality, there are some wait lists that you can sign in, and then if somebody moves, you can go in. And yeah, the study of the aftermarket for these mechanisms is also something that is interesting. You know,
Narita has a paper on that.
Yusuke has a paper on that. Yeah, Yusuke Narita has a paper on that. Yes.
Are there papers that take into account potential heterogeneity in beliefs across income classes or gender? Heterogeneity in bias, that some poorer households have more biased beliefs in terms of underestimating.
Oh yeah, so I think that for that, okay, so in our paper we have that people with different demographics may have different preferences. Now, if you think about it, how demographics affect beliefs and how well they strategize, then this paper by Kapoor, Nielsen, and Zimmerman, that's exactly that. They show that mistakes correlate with demographics, essentially. Yes.
I would think that fairness is one of the main driving forces behind such designs. Isn't perhaps minimum student utility a better measure of how well a mechanism does?
Yeah. No, I look. Yeah. So that's why a lot of things that people do is here. We basically say, okay, what if? How many people are worse off? How many people are better off? How many people? But yeah, you're saying what is the what is utility of them? Well, like a Rawlsian, like extreme Rawlsian version where you say, oh yeah, you could even, I mean, Dan is probably going to talk about that, but you could even try to weight outcomes differently. Where it's not the minimum, it's just some adjusted social utility function. Yeah, yeah, you can do that. Okay. Yes.
So would estimation subject to an equilibrium constraint be feasible, or have you tried to solve this equilibrium problem?
Oh, you mean as a way to solve for the equilibrium?
Yeah.
Interesting. Yeah, I think that would be the first, one of the first things that I would try if we wanted to solve for the equilibrium of the Bayesian game that this manipulable mechanism integrate.
Could you do it like an iterative, like these moment-based Markov models where you make a guess, solve, and then simulate it, keep doing that until...
Yeah, you're thinking about a sort of an atonement process that is going to go from cutoffs to then reports and then cutoffs, reports, cutoffs, reports. Yeah.
But sorry, so just to try to understand this. So this is like GPV.
What we did is
Right.
Yeah, the analogy of what we did is we estimated a first price auction using GPV and then it simulated what would happen in a second price auction. Meaning that the counterfactual is strategy proof.
Yeah, but
you're asking is, can you also
do a not strategy? Yeah.
Do a like another first price auction? Yeah. Another manipulable mechanism that is different. No, I think that I would go in that route, but yeah, I don't know. Yeah, we haven't done it. Yeah.
You know, just like the Vickery auction, even though it says to be, you know, top, some people don't report truth, they overbid, right? So is it possible that deferred acceptance, you could detect people still manipulating even they're not?
It shouldn't be. Yeah. There are some papers that find some evidence of that going on. Yeah, I agree. Yes.
As I remember, Kapoor paper was simulating equilibrium for Boston mechanism by converging the cutoffs of and for Boston mechanism.
Yeah.